In this video, we discuss learning outcome number 3 for lesson 5.1, which is all about finding the population mean, variance, and standard deviation given a probability distribution. I'll also describe the rationale behind the formulas. Now remember, when you're using a probability distribution, we're actually finding parameters, population parameters, and not sample statistics. The probabilities in our probability distributions come from that classical approach to calculating a probability. When we're using that classical approach and we've got all of the possible values of that random variable x, the data in that table describes a population, not a sample. So the mean, standard deviation, and variance that we calculate in this case describes the population, so we call those parameters. These are not the sample mean, the sample standard deviation, and the sample variance, because there is no sample. This is talking about what we expect to happen. So these are giving us theoretical mean, standard deviations, and variance for that population. Now, if you want to compute the parameters for a probability distribution, this is the notation. Remember, mean is represented by mu whenever you're talking about the population mean. The population variance and population standard deviation are represented by sigma squared and sigma, lowercase sigma, respectively. And they're calculated using these formulas. In order to find the mean, you'll take that value of the random variable x and you'll multiply it by the corresponding probability. You'll add all of those together, and that's going to give you the mean. Now, if we're calculating the variance, what we're doing is we're trying to measure that variation in our data, or that the variation in those probabilities. So what we do here is we take each x value, so that's each value of our random variable x, and we subtract the mean. So that's giving us a deviation from the mean. Now, we don't want those deviations to be signed. So if x is greater than mu, this difference would be positive. If x is less than mu, that difference would be negative. But we don't really care about whether we are above or below mu. We want to count all deviations from mu as positive. So one way that we do that is we square that deviation, and then we multiply by the corresponding probability, and then you multiply those together and you add those up, and that gives you the population variance. This is a formula, or this is a format that's easier to understand because it has that x minus mu in it. That's that measure of the deviation of that random variable x from the mean. Now, in practice, we don't tend to use this formula. We use this formula instead. This one's easier to evaluate, and it's equivalent to the formula above. So if you are doing hand calculations, I would use the second one, or even if you're using Excel to do the calculations, it's easier to come up with the correct columns in Excel if you use this second formula rather than the first one. So I highly recommend that you use the second one. They are equal to each other. And then lastly, if you want the standard deviation, you just take the square root of the variance. Now we've got a new term. This is called the expected value of a discrete random variable. This is represented by the capital E. This expected value is the theoretical mean value of infinitely many trials. So if you did this infinitely many times and then you were able to calculate the mean value, then you would get this expected value E. So the mean and the expected value are the same thing. So if someone asks you for the expected value, all you have to do is compute the mean. So you take the x's, you multiply by the corresponding probabilities, and then you add them together. So again, the way we interpret expected value, or the way we interpret the mean, is that this is the average value we would expect if we were to repeat that procedure indefinitely. This reminds me of the law of large numbers, which we discussed in lesson 4.1. The law of large numbers said that as a procedure is repeated, the relative frequency probability of that event tends to approach the actual probability. So that's what we're talking about here. For example, if we flip a fair coin just once, there's a probability of getting heads of 1 out of 2. Now, if we flip it 6 times, we might think that since the probability is 1/2, we'd get 3 heads out of 6, but there's no guarantee of that. But if we continue to do this, and we do this over and over and over again, and every time we're counting the number of heads we've gotten so far and counting the number of heads, and then we're looking at that ratio over a really long time, that relative frequency will tend to approach the actual probability, which is 1/2. Now, when you look at expected value, it's using that same idea. The only difference is that in general, you don't have just 2 possibilities, heads or tails, or 0 heads or 1 head. You might have 2 or more values for that random variable x. So you're going to take each value of that random variable x, multiply by the corresponding probability, add them together, and then you'll get the expected value. So it's just like what we were talking about with flipping that coin, but you don't just have 2 outcomes, either 0 for getting tails or 1 head for getting, or 1 head if you, you flip heads. Now you might wonder where this formula comes from and why we should use this formula. It's important that we not just blindly apply formulas. It's helpful to understand where they came from. So one rationale that we'll use for this new formula for the mean is to look at the following formula for the sample mean that we had for this approximation of the sample mean when we had a frequency distribution. Now remember, the sample mean is the sum of all of the x values you have divided by the sample size. Now we said that if we had a frequency distribution, so we don't actually have the data values themselves, we could approximate the value of all of the x values in a particular class by that class midpoint x. So in this formula here in the middle, x does not represent a value, it represents the class midpoint. So we took all those class midpoints, we multiplied them by frequencies to get an approximation of the sum of the values in that class. So that's an approximation of the sum of the values in that class, and then you add them all up, so you have the sum of the values in all the classes, which is an approximation of this numerator over here. And then you divide by the sample size. Well, this n, the sample size, is a constant. So if you wanted, you could pull that inside the summation. Now, some students are like, I don't know. Well, just think about it. If you have this whole thing and you're dividing it by 100 at the end, and it's a sum with a whole bunch of terms, couldn't you divide each one of them by 100? Hopefully you remember from algebra that if you're dividing by a monomial, that's legal. That's exactly what we're doing as we go from here to here. We're saying if I'm dividing everything by n, if I add all of these up and then I divide by n, that's the same thing as if I took that x times the frequency and divided by n. But taking x times the frequency and dividing by n is the same as taking x and multiplying it by the frequency divided by n. But now let's think about what that frequency divided by n means. That is the number of x values, the number of data values in a particular class divided by the total sample size. So let's say that there were 17 out of 100 that were in a certain class. Well, then 17% of those values lied in that class, or the probability of getting a value in that class, according to the relative frequency approximation, would be 0.17 or 17%. So 17% in percentage form, 0.17 when we're looking at actual probabilities. So this F over N, it's kind of like a probability. It's the relative frequency. It's the proportion of the sample in that particular class. So we'll take the proportion of the sample in that class and we'll multiply by the class midpoint. That's what this formula says to do. Now with probability distributions, it's a little bit different, but there's a lot that's very similar. And here we're talking about discrete probability distribution. So our x values are going to take on a finite number of values that we can list. The number of x values is countable. Now here with discrete probability distributions, rather than having a range of values corresponding to a class, we have a single value representing that random variable x. Now, because we're talking about probability distributions, rather than using the sample size n, probabilities deal with the whole population. So we're going to use the population size, capital N. Then in this case, that f divided by n, where we're using capital N in the denominator, is the probability of getting that value x of that random variable. This is where f would be the number of times that the event x occurs in infinitely many trials, because that's the true probability. That's that classical probability that we calculate and then put into our table. And after a really long time with infinitely many trials, according to the law of large numbers, that's exactly what we expect to get. So we've got this approximate sample mean given a frequency distribution over here. If we replace the sample size lowercase n with the population size capital N, and if we think of this x value as the value of our random variable rather than the class midpoint, what we get is this expression over here. This is not giving us the sample mean, this is giving us the true population mean. If we take f divided by capital N, that's giving us the probability that the value of our random variable is x. And we take that probability and we multiply it by the corresponding x value and we add them together, and that's giving us a mean in much the same way that this formula in the middle over here on the left-hand side approximated the sample mean given a frequency distribution. Let's actually practice using these formulas now. The example says, or in this example, we're going to find the mean, variance, and standard deviation. And here's our problem statement. It says, 5 males with an X-linked genetic disorder have 1 child each. The random variable is the number of children among 5 who inherit the X-linked genetic disorder. So if there are 5 children, or 5 males that have children, it's possible that 0 of their children inherit the genetic disorder, 1 of their children inherits the genetic disorder, or 2, 3, 4, or 5 children out of those 5 children inherit the genetic disorder. And these are the corresponding probabilities. We saw these when we were looking at probability distributions in the last learning outcome. Now we're just asked to find the mean, the variance, and the standard deviation. So we're going to use our formulas. To find the mean, we're going to use this formula. In order to use this formula, if I've got x's and probabilities, I'm going to add a column to my table. What I need is x times the probability. That will go over here. So we're going to create a column for that. And then once we create that column and then multiply the x and the p to fill in that column, we're going to add the values in that column, and that will be the mean. So let's do that on a piece of paper. I'll share my paper with you. Okay, so this is what we have. Now we want x times that probability in this column. Well, 0 times anything is 0, and 1 times anything is just itself. 2 times that gives us that, and 3 times that is that. 4 times that it's 0.624. And then 5 times this is 0.155. Okay. So we're just multiplying and then we add. So when I add these up, I've got the sum of the x's times the corresponding probabilities. That's 2.9 or 2.497. Now I want to show you how to do this in Excel as well. So I will share my screen with you. Now, once we're in Excel, we can type the values for our random variable x over here. So we have 0, 1, 2, 3, 4, 5. And the probabilities were given, so I'll do the data entry there as well. So that's x, and that's the probability of getting x. There we go. And then I want x times that probability here. So I hit equals, and then I grab that cell, and then use the asterisk for multiplication, and then I grab that cell, click enter, and then drag and drop that corner there. And then we want to add those up. So in this box, I'll type equals sum, open parentheses, select those cells, close parentheses, and you get 2.5. Ooh, I must have typed something in or written something down incorrectly because I did not get 2.5 when I did this on my piece of paper. So let's go back to my piece of paper. (0.156 plus, oh, I see what I did. That should be 626, not 623. 0.626, 0.939, 0.624, and 0.155. Okay, so now I get 2.5 again. That should agree with what we get in Excel. That's why it's always good to do it both ways, or to do it and compare your answer to your friend's answer and see if you guys get the same thing. Okay, so that's what I got here, and that's what I got when I typed up these slides. All right, so we just found the mean. So that's a mean of 2.5 children. Now you might be saying to yourself, how can we have an expected value of 2.5 children? Well, just remember, it's like an average. So even though you can't actually have 2.5 children, it's possible that if you were to take the mean with infinitely many trials and you had groups of 5 men that had this X-linked genetic disorder, and you just kept looking at frequencies, after a really long time, the mean would be 2.5. With infinitely many trials, that's what you would get. You'd get 2.5. Okay, so now let's look at the formula for the variance. Now you've got 2 formulas for the variance, but one of them is easier to use than the other. So we're going to use the one that's the easiest. So we're going to use this one. Now notice that in the formula you've got an x squared and the probability of x, and then we're subtracting that mean squared. So in order to calculate that x squared times the probability, first you need to create an x squared column, and then you want to take the x squared column and multiply it by that probability column. Then you want to add the values in that x squared times the probability column. That's what gets you that first term in the variance formula right here. And then you want to subtract the squared mean. Let me show you how to do that in Excel. So I want x squared in this column, and I want x squared times the probability of x right here. So here I would type equals, and then I'd grab the x value, and then you can use caret 2 to square it. 0 squared is, of course, 0. And that's good. It gives me all those numbers squared, which is just what I want. Now, you could probably do all of that in your head. You really don't need Excel to calculate those for you, but it's always good to type it in and see if you get the answer that you expect, just in case you're prone to making little mistakes like I am. So you've got these x squareds here, and you want to multiply them by the corresponding probabilities. So we'll type equals, and then we'll grab the x squared, and then asterisk for multiplication, and then multiply by the corresponding probability. Hit return, and then just drag and drop. And then we want to add all of those together. So I will type equals sum, open parentheses, highlight that cell, grab that bottom corner, close parentheses. Now that is not our variance. We've got to take that number and subtract the mean squared. Now the mean was over here. And so we get 1.246 as the variance. Now, the units on the variance are a little weird. They're not the same units as the random variable x, but they're the units of the random variable squared. Since the random variables units were children, these are children squared, which is a little odd. Oops, that's not what I wanted to do. There we go. Trying to get back to my PowerPoint. All right, there we are. And we get the 7.496. We subtract the 2.5 squared, and we get that 1.246 children squared. Now, if you want standard deviation, this is a measure of the variation in those probabilities. You just take the square root of that answer that we just found. So we had that 1.246 children squared for our variance in the last slide. Take the square root of that, and you get 1.116 children. Now, if you want to interpret these numbers, the mean can be interpreted this way. The mean is the number of children or the mean number of children that inherit a genetic disorder among 5 possible children is 2.5 children. Now, also we can interpret it this way because it's expected value as well. If we were to collect data on a large number of trials with 5 parents with single children in each trial, meaning each parent would be associated with 1 child, then you would expect to get a mean of 2.5 children that inherit the genetic disorder if you were to calculate the mean over a large number of trials, infinitely many trials. So this is related to that law of large numbers that we talked about. So that's it for learning outcome number 3. I'll see you in the next video to discuss the range rule of thumb.